So now we're going to take a look at some algebraic examples of determining the shape of the graph. And the way we're going to do that is we are going to find transition points. Remember, transition points are essentially points where we have local mins or maxes. So think about how we're going to do that. We're going to be looking at critical points where the derivative is 0 or undefined. And then of course we'll need to do a sign check of the first derivative to help with that. And in fact, we're going to find intervals of where we increase or decrease the location of local extrema. So that's all going to come from the first derivative. And then we'll talk about concavity and location of points of inflection, which are also transition points, and find out where a function's concave up, concave down with the second derivative. And then do we have any asymptotic behavior of the given function? Is there horizontal or vertical asymptotes? And so we're going to put everything together and see if we can sketch the graph. We'll do this in a certain way, and essentially the way we were doing a sign check on the first and second derivative and then giving the shape of the graph from that. So let's start with the easy polynomial function. Again, it's always good to cite what the domain is. And for polynomial functions, the domain's all real numbers, so that's good. We want to look at everything. And so obviously what do we need to do is find the first and second derivatives, right? I mean, at this point in the game, if you don't know what to do, always a good start, right? But we will need this to talk about where we have potential transition points. So f prime of x equals what? 3x squared minus 18x. Let me go ahead and factor that because that will help me find where the derivative is 0. And factor out a 3x from that, leaving me a x minus 6. I'm going to find the second derivative. The derivative of this function is going to be 6x minus 18, which I can factor out that 6 to help with that. And so what I want to do now is look at a sign check. And so my sign check, domain is all real numbers, so I'll stretch this line through all real numbers. And then clearly the first derivative is equal to 0 when what? When x is 0 and 6. And the second derivative is 0 when x is 3. So let's just see what's happening at those points. So at 0, at 3, and at 6. And so what I would start with is, essentially, these, see what's happening to the sign of our first and second derivative in these 4 intervals, right? Everything less than 0, between 0 and 3, between 3 and 6, and everything greater than 6. So if I look at my first derivative, here's my first derivative. I can use this or this factor form. If I plug in something less than 0, like a -1, I'll get -3 times -7. Negative times negative will give me a positive. Notice it's 0 at 0 and 6. So I'm going to go ahead and put 0 right above 0 and 0 right above 6. Between 0 and 6, it's the same sign. So like for instance, if I plug in 3, 3 times 3 is 9. 3 minus 6 is -3. Positive times negative is negative. So it's negative in this whole interval, but I want to sort of emphasize in this interval and this interval it's negative. And then for values greater than 6, like 7, I get 21 times 1, I get a positive result. So there's the sign of f prime. If I then go and look at the sign of f double prime, of course again it's 0 at x equals 3, so let's put a big 0 for that. And for values less than 3, if I plug in like 0, I get 6 times a -3, that's -18, it's negative. So it's negative for values on these 2 intervals. And if I plug in something greater than 3, like 4, I get 6 times 1, I get a positive number. Second derivative is positive in these intervals. So just doing a sign check of both the first and second derivative. And notice, that we have transition points at 0, because I have a change in sign of my first derivative. And of course, we kind of know what's going on there, right? We're going to have a local max there, and then a local min at x equals 6, and change in what? Second derivative means change in concavity at 3. And so, we can now say, the transition points are those values there. Now, what about the shape of the graph? So just like we were doing in the previous video, we're going to use that double sign notation. So this region, we're plus minus shape, right? Derivative is positive, second derivative negative. This means we're what? Increasing and concave down. So the shape looks like that. Negative, negative, decreasing, concave down. First derivative negative, decreasing, second derivative concave down. So we look like that. Decreasing, concave down. Minus, plus, decreasing, concave up. Whoops, that's not correct. Decreasing, concave up. I drew increasing, concave up. And then plus, plus, increasing, concave up. That's where I want this piece here. Okay. And you can sort of see, we talked about we had a local max at x equals 0, and you can see we're reaching that max, right? And then we have a change in concavity, right? Concave down to concave up at 3, and then you have this, what? Minimum at x equals 6. So we can see all those things. So we can answer all these questions that we ask for, the intervals of increase, decrease, location of local extrema, concavity, location of points of inflection, etc. But, also we can tell on the interval for values less than 0, we are, right, increasing, concave down, and so on. So we have the actual shape on these intervals. But we'll just summarize everything that f is increasing, where the first derivative is positive, so that's values less than 0 and greater than 6. F is decreasing on the interval, that's decreasing there, on the interval where what? It is negative from 0 to 6. And F has local max where we change sign in the first derivative from positive to negative. Notice you could also use the second derivative test because the second derivative is negative there. So with that critical point being 0, if you remember by the second derivative test, if the second derivative is negative, meaning we're concave down, then we have a local max at 0. And then F has a local minimum where the first derivative changes sign from negative to positive, decreasing and increasing at x equals 6. As far as concavity, F is concave up on the interval where what? The second derivative is positive, where the derivative is increasing. So that's going to be for values greater than 3. Everything greater than 3. And then everything less than 3, the second derivative is negative, and so we're concave down. And F has inflection point at what? X equals 3, because we're changing from concave down to concave up. We have a sign change in the second derivative. So this summarizes everything for us. We can talk about all these things here from the sign checks of the first and second derivative, and then we can talk about the shape, right, on each interval where it's increasing concave down, decreasing concave down, decreasing concave up, increasing concave up on those respective intervals. And it, so then if you want to take a look at the graph of the actual function, how can we finish that off? Well, we can find some anchor points. How do we do that? We can find a y-intercept real easy, and sometimes an x-intercept. Y-intercept's easy, right? If I plug in 0 into the function, right, the output is what? 10. Plug in 0, I get an output of 10. Finding the zeros might be a little hard because I got to solve a cubic equation, but in general we can try and find x-intercepts. And we can just plot some other points. There's no vertical or horizontal asymptotes for the polynomial function. We can talk about end behavior, knowing it's a degree 3 polynomial, right? Its end behavior and its coefficient of the leading term is 1, that its end behavior is just like x cubed. So as x goes to infinity, this is going to infinity. As x goes to minus infinity, this is going to minus infinity. But again, the important features in the graph are shown here, and we find the location of our local max at x equals 0, local min at x equals 6. We're increasing for values less than 0, increasing for values greater than 6, and decreasing between 0 and 6. And we have an inflection point at x equals 3, so right here, there is our inflection point. Concave down for values less than 3, concave up for values greater than 3. So just confirming all that information as we look at the graph of, there we go, it looks better, graph of the function. Okay, so that's the way we will algebraically analyze a graph. Let's look at a couple more examples. This is not a polynomial function, it's got a square root involved in it. And notice the domain is affected by that because of the square root of x. What's our domain for this function? It's everything greater than or equal to 0, right? Because we include 0 into that sort of an endpoint on the domain, which kind of is important. You know, can 0 be a transition point? Well, I mean, there's nothing less than 0, so technically it's not really a transition point. But it is important to know that we don't want to answer any questions and say, you know, this function's increasing or decreasing or concave up for any values that are less than 0. So it's real important to have the domain here. So of course I'm going to rewrite this as what? Y equals x minus 4 times x to the 1/2 power, right? So then I can find the first derivative. Derivative of x is 1. And this is what? Bring down the 1/2, x to the negative 1/2. So if I clean this up, 1/2 times 4 is 2. X to the negative 1/2 is 1 over x to the positive 1/2, or the square root of x. I'll just write it that way. Now, to find out where this is 0, I think some of you can look at this and tell me when that will happen. But in general, I can write this as one fraction is one way to do it. So 1 is equal to what? The square root of x over the square root of x. And now I can combine the numerator. Okay, so the derivative is undefined when x is 0, but obviously, you know, we've got an endpoint there. So again, that's not something we want to include. I mean, we're going to start at 0 anyway, so, but clearly it's undefined when x equals 0. But when is the y prime going to be equal to 0? Well, when the numerator is 0, when the square root of x minus 2 equals 0, or when the square root of x equals 2, or when x is what? 4. Okay, let's look at the second derivative. I'm going to use I'm going to rewrite this, right, as 1 minus 2x to the negative 1/2 in order to find y double prime. Derivative of 1 is 0, and then I've got minus 2, and then the derivative of x to the negative 1/2 is negative 1/2 x to the negative 3/2 by the power rule. So this negative times negative is positive, 2 times 1/2 is 1. I'm just left with x to the negative 3/2, or 1 divided by x to the 3/2. And notice that that's never equal to 0. I cannot divide into 1 and get 0. It's undefined when x is 0 again. Okay, so really the only potential transition point is x equal 4. And let's see if that indeed is a transition point. So I'm going to do a sign check on the first and second derivative, and notice its domain is everything greater than 0, so I'm only going to look at this and 4 right here is the point of interest there. So let's look at the sign of the first derivative. We know it's at 4 it was 0, right? We said at 4 the first derivative was 0. And let's look at values between 0 and 4, like if I plug in 1, square root of 1 minus 2 is a negative 1 over the square root of 1. Negative 1 divided by 1 is negative. So the first derivative is negative. And then for values greater than 4, like 9, square root of 9 is 3. 3 minus 2 is 1. I get 1/3 positive though. Okay. So notice we have a transition point. You know, x equal 4 is transition point. In fact, it's the only transition point, because we see a change in sign in the first derivative at x equal 4. The second derivative now, let's think about it. For any value of x, notice I'm going to be plugging in, remember, only positive values, right? If I take any positive number and raise it to the 3/2 power, the result is positive. So the second derivative is always positive. So positive, positive there. And so to complete, we can talk about the shape of the graph of y. Here it's minus plus, right? First derivative is negative, second derivative positive, so we're decreasing, concave up. Here it's plus plus, increasing, concave up. So basically, I mean, there's your basic shape in general for the graph. And we can answer all our questions about where is y increasing and decreasing. Y is increasing on what? The interval where the first derivative is positive. Y is decreasing on the interval where the first derivative is negative. And this is real important, right? It's not minus infinity to 4, right? Because we start at 0. That's real important. Why it's important to start with your domain, right? Make sure you understand the domain is only positive values. Otherwise, you'll get some erroneous results here. Does y have a local maximum? Did we ever change sign from positive to negative in the first derivative? No. Y has no local max. Does y have a local minimum? Yeah, change the sign in the derivative from negative to positive, decreasing, increasing. Y has local min at x equal 4. What about concavity? Y is concave up, where the second derivative is positive. Well, that's on the entire domain, which is everything greater than 0. And y, therefore, is never concave down. Since we never change concavity, y has no inflection points. Okay. Now, there is something of interest in terms of vertical asymptotes. What's happening right at 0? What's happening at 0? What are we approaching? Well, I can plug in and find out, right? So it's continuous from the right at 0. If I plug in 0, I get 0 minus what? 0. I get 0, right? So as we're approaching from the right, this thing, right, is right, going from right to left, right, we're going this way, and then back up, and we're approaching 0 there. We're approaching 0. Again, I can plot some points to help flesh it out, but here's the graph of that function, and you can see there's the point 0, 0 that it dead ends at, so to speak. And we have our local min right here at x equal 4, as we indicated, decreasing between 0 and 4, increasing from 4 to infinity, always concave up, no points of inflection. Do one more example. This is going to be a trigonometric function. And notice it's on a closed interval. The domain for this function is all real numbers. The reason we're going to do it on a closed interval is because of the sine function. The periodic nature of this causes us to have an infinite number over its entire domain, infinite number of intervals where it's increasing, where it's decreasing, concave up, concave down, etc. So we'll just look on this interval. So I'm going to find the derivative. Derivative of sine is cosine. Derivative of 1/2 theta is 1/2. Okay, and so first of all, the first derivative is 0 when what? Cosine theta is equal to 1/2. When it's equal to 1/2, the difference is 0. Where does that occur? On the interval from 0 to 2 pi. That occurs at pi over 3 and at 5 pi over 3, where cosine is positive in that first and fourth quadrants, right? Think about the unit circle and make sure you can get those exact values from that. Second derivative, derivative cosine, negative sine theta. So when is the second derivative equal to 0? Well, just when the sine function is equal to 0. And that occurs when what? Theta is either 0, pi, or 2 pi. Keep in mind 0 and 2 pi are the endpoints, and so technically for our interval they're not really transition points. So the transition points potentially are pi, pi over 3, and 5 pi over 3. Let's see if we do have sign changes in the first and second derivative there. So I've got a closed interval from 0 to 2 pi to show my sign checks on, and I'm interested in pi right in the middle there, and I'm also interested in pi over 3 and 5 pi over 3. So 1/3 is pi over 3, and 5/3 about here, 5 pi over 3. So if I start with the g prime, let's just say the sine of g prime, it's 0 at pi over 3 and 5 pi over 3. Let's plug in pi. If I go back to the derivative, cosine of pi is -1. -1 minus 1/2 is -1.5. Important thing is it's negative on this interval. And I'm going to do these like I've been doing, these potential transition points here. So again, it's negative on this interval and this interval, everywhere between pi over 3 and 5 pi over 3. Now, if we look between 0 and pi over 3, what do we know? Cosine at 0 is 1. By the time it gets to pi over 3, it's equal to 1/2. So it goes from 1 to 1/2 over that interval. So that means cosine is bigger than 1/2, but of course less than or equal to 1 on this interval. Okay, so if we think about that, so cosine theta is bigger than 1/2 on that interval, then this difference is positive. So I can just plug in values to determine the sign of the first derivative if I want to. Similarly, we'll see it's positive on this little interval as well. What about the sign of the second derivative? Second derivative is 0 at 0 at pi and at 2 pi. I'm not going to put the endpoints. It's 0 at those points. But just what is it in these intervals? Well, it's equal to the sine of SIGN of the second derivative. The SIGN, the sine of it, is the opposite of the sine SIGN of the sine SINE function. Ooh, that's crazy. It's the opposite sine of the sine. Okay, does that make any sense? All right, so remember the sine function normally at 0, 0 goes up to 1 at pi over 2, back down to 0 at pi, and then goes to -1 at 3 pi over 2 and back down to 0. So remember the sine function looks like that. But our graph is negative sine theta, which is a reflection in the x-axis. So it's negative between 0 and pi, and positive between pi and 2 pi. So our second derivative is going to be negative between 0 and pi, and positive between pi and 2 pi. Okay. And so what's the shape of our function g then? From 0 to pi over 3, it's plus minus, which means it's increasing concave down, looks like this. Minus minus, decreasing concave down. Minus plus, decreasing concave up, going down but concave up. And plus plus, increasing concave up. So do we have transition points where transition points are going to be at pi over 3? We have sign change in the first derivative. At pi, we have a sign change in the second derivative, and at 5 pi over 3, sign change in the first derivative. So the transition points are theta equal pi over 3, pi, and 5 pi over 3. Again, if you include 0 and 2 pi, technically we won't worry about them because they're the endpoints. We're just focused on this interval because of the. If we were looking at the domain of all real numbers for this function, yeah, they would be transition points. Okay, so now we can answer all our questions about when is g increasing where the first derivative is positive. So that's from 0 to pi over 3, and then from 5 pi over 3 to 2 pi. G is decreasing where its first derivative is negative. That's between pi over 3 and 5 pi over 3. Does G have a local max? It does. Where's it having local max? Where the derivative changes sign from positive to negative at x equal pi over 3. And then G has a local minimum where the sign changes from negative to positive in the first derivative. What about concavity? G is concave up on the interval where the second derivative is positive, so that's greater than 0. Greater than 0. Yeah, greater than this. Greater than pi up to 2 pi, sorry. From pi to 2 pi, the second derivative is positive. And then from 0 to pi, the second derivative is negative. So G is concave down on that interval. 0 to pi. And do we have an inflection point? Yeah, we do. Do we have change in concavity? Yeah, we say right here, it changes from concave down at pi to concave up. So at x equal pi. Okay. So again, on the interval from 0 to pi over 3, we're increasing concave down. Pi over 3 to pi, we're decreasing concave. Let's say increasing concave down, yeah. Decreasing concave down. And then from pi to 5 pi over 3, decreasing concave up. From 5 pi over 3 to 2 pi, increasing concave up. You can see the shape of that graph. Again, we can plot points to help us out. Here's the graph of that actual function. And we can see all the information we have here is consistent with the graph. Again, pi, about 3.14 is right there. There's pi. 6.28, there's 2 pi, just for reference. Pi over 3 is a little bit more than 1. So there's pi over 3, and then 5 pi over 3. The location of our local min, as we said there. So there it is. And so, this is sort of, in a sense, this section is bringing together everything that we know about from previous sections about what the first and second derivative tells us about the graph of the function, as well as other things that we can do from pre-calculus and analyze the behavior of the functions from that. Support, though, I want to see certainly for these problems as a sign check, and then I might even ask on this interval is increasing concave down, together, what's happening to the shape of the graph in these sections. All right, so our next section we're going to look at is going to be applied optimization. That's the last topic for the course. So the next lecture video set will be our last, but a very important one, and I really enjoy it, so I'm looking forward to it. It's going to be a lot of fun, and we'll finish out with that.